In this video presentation, I will demonstrate how to analyze the well performance data for an unconventional oil example. This production data comes from the Bakken. The well is a multi-frac horizontal well. Let's take a look at the data. Harmony has a production plot which can show any combination of ratios, production values, pressures, and many other features that we want to show. On this plot, we have gas-oil ratio, run depth pressure, operated oil rate, operated water rate, and measured tubing and casing pressures. Let's take a look at the data editors. Of specific interest in oil example is the oil properties. We need to make sure that the bubble point pressure is correct. This makes a huge difference when interpreting original oil in place volumes. Very often in production analysis, we don't have access to detailed PVT properties that are measured in a laboratory, and this is one of those cases. So what we can do is use the correlations that are available inside Harmony to predict the bubble point pressure. However, this requires calibration from actual well performance data. So what we want to do is go back to the diagnostic plot and take a look specifically at the measured gas-oil ratio. This is very important in oil examples. What we're looking for is to see whether the gas-oil ratio is constant and also to see what its value is. In this case, we can see it's somewhere in the region of 1200 standard cubic feet per barrel, and it's relatively constant except at the end where it starts to fall. This is a very good indication that the reservoir pressure is still well above bubble point pressure. Let's go back to the data. As we can see, I've entered into the correlations a solution gas-oil ratio of 1200 SCF per barrel, and this predicts the bubble point pressure that we use in the correlations. This is how we calibrate the model to make sure that we do the correct oil analysis when we're analyzing this well. Let's take a look at the Wellbore information. We can enter in casing, tubing, perforated intervals, and this is how we calculate the bottom hole pressures in Harmony. The production table shows us a columnar display of all of our data and also our calculated sand face pressures. We will need these to do a proper analysis inside Harmony. Now we're ready to analyze. Let's go to the analysis page. In Harmony, there are a selection of a number of different analysis methods that are available for use. They're organized by application. We have some for Decline Plus and we have some for Fast RTA. We're going to use several of these different methods to analyze the well performance for this unconventional oil example. We're going to start with the simple methods and move towards the more complex methods. Let's start with the decline curve. So we're going to create a oil rate versus cumulative oil example. And create a new analysis. Okay, there's our decline analysis. This is an exponential decline. We can change the decline rate by moving the curve up and down this way. We could also do a best fit of the data using our best fit selection tools here. And this is a nonlinear regression best fit. It will fit a generalized hyperbolic curve to the data. This gives us a good place to start and gives us an estimate of what the ultimate recoverable reserves we should expect to see for this well. Maybe we'll create another analysis here with a low case. So we have one for exponential decline and one for a more hyperbolic decline. So it looks like we're ranging somewhere in between 90,000 standard stock tank barrels and 160. I'm going to rename this tab Decline Curve Analysis. We can call it whatever we want. Let's take a look at another analysis method. Of interest are type curves. We're going to take a look at a Fekete type curve for this oil case. I'm going to filter out some of these extraneous data points first to make it a little easier to see. And we're going to normalize the data with pressures. The type curves are useful because they can tell us whether we're in transient flow or boundary dominated flow. In this example, we're still in transient flow because the slope of the data is shallower than the limiting decline curve here, which is the harmonic decline curve. That tells us we're still well in transient flow. For transient flow, we're going to use the Wattenberger type curve. And again, we'll eliminate some of these extraneous data points. The Wattenberger type curve is a linear flow analysis method. If we set up the data, we can see it fits very nicely on the half slope, which is an indication of linear flow. We can move that data as far to the right as we can, and we have a good match. In addition, we can include the raw data derivative on here. This confirms that we have linear flow. Both of these curves are half slope. I'm going to rename this plot and call it flow regime identification. That way we will know later when we come back to this that we used this plot to determine that we had linear flow. We can also put a note in the comments box that says linear flow. Let's move on. The next method of interest would be the unconventional reservoir module. We're going to pick one for oil variable pressure. In this module, we can do a production analysis all the way through to forecast in one step, as all of these analyses methods are linked together. As we can see, we can change the slope of the line on the square root of time plot, everything else changes. We can also change the extrapolation on the flowing material balance plot, and everything adjusts accordingly. So what we're going to do is start by getting the best straight line analysis on this plot, taking careful consideration into ensuring that that line goes through the origin. So I'll move that pivot point down to the origin and basically dial in where I believe that straight line analysis should be. So it's going to be somewhere in there. The second part of this is we have to make sure that the dotted green line goes through the end of the data. This is all transient linear flow. This line marks the end of transient flow, so it should be at the end of our data. We can adjust that by changing the slope of the flowing material balance plot, just like this. So that is now our interpretation, and we have a production forecast that goes along with that. Production forecast is shown in red, and I would call this our P90 reserves. The reason I call it P90 reserves is because the dotted green line is right at the end of the data, which is an indicative of the minimum oil in place, or the minimum recoverable oil. So I'm going to change the name of this to P90. Now we're going to take a look at our horizontal multifrac and interpret some parameters out of this analysis. The square root of time plot only gives us the A root K product. So we're going to try and make a more detailed model out of this, and the parameters that we get as a result we can use to seed the analytical model for history matching. We can start by entering the horizontal well length for this well, the number of fracture stages, and the program will calculate the matrix permeability that results from that. That's consistent with this area. Now we're ready to do a history match analysis. So I'm going to create another analysis method here. And this is going to be an analytical model for oil, and it's going to be horizontal multifrac composite. So we can fill in the parameters for this by using the default button. And we're going to use our P90 results. And this is our pressure history match as a result. It's not quite matching the data, so I'm going to fine-tune the match by doing our automatic regression. And it shouldn't take too long for the model to settle into a minimized match, minimizing the error between the simulated pressures and the actual pressures. So that's pretty much ready to go. We can stop it there, and we can do a forecast. The forecast is a little bit off here because our pressures aren't quite matching. I'm going to fix that by putting in the right pressure, which should be somewhere around 2900. And now we have a reasonable looking forecast. I'm also going to put an abandonment rate in here of 3 barrels per day. I'm going to do the same thing for my P90 forecast over here. I'll change the name of this one as well. We'll call it P90 Analytical. So we have our P90 reserves from our simplified model, and we have our P90 reserves from our full analytical model. Now what we might want to do is compare all these forecasts together. In Harmony, this is very easy to do. I simply go back to my decline curve analysis. All of the analyses that I have done now are part of this interpretation and can be displayed on this plot. So I'm simply going to show my P90 analysis and my P90 analytical. And they're now part of the forecast and they can be compared together.